Imagine you're trying to simulate something complex in the real world, like uh, groundwater flowing beneath your feet, maybe.
Or how heat moves through an engine block, or even the stresses on a bridge structure. Yeah.
These aren't simple systems, right? They're
Mhm.
often described by these, well, tricky equations called partial differential equations, or PDEs.
And crucially, the real world is messy. The ground isn't just uniform rock. The engine material, might have microscopic flaws.
Right, impurities.
The bridge material isn't perfectly consistent. And all that introduces randomness or uncertainty into those equations.
Right, so you're dealing with PDEs that have random inputs. These are often called stochastic PDEs or SPDEs. And if you want your simulation results to actually be useful, you absolutely have to understand and quantify that uncertainty.
You need to know, how does the fuzziness in your input affect the fuzziness in your output? The
Exactly.
classic way to tackle this is Monte Carlo simulation. You run your model lots and lots of times, each time picking random inputs according to their probability.
It's intuitive, sure. Like flipping a coin a million times to understand the odds. It
Wow.
works. But wow, is it slow?
It really is. To get a clear picture of the whole range of possible outcomes and their likelihoods, you need so many runs. It can take forever, computationally speaking.
Yeah, impractical sometimes.
That's where methods like the Stochastic Galerkin finite element method, or SGM, come in. It's a different philosophy. Instead of running tons of separate simulations,
Hmm.
SGFM transforms the entire stochastic problem, the PDE, with randomness built in into one single, much larger deterministic problem.
Okay, hold on. So it takes the randomness and somehow wraps it all up into one giant equation set.
Yeah.
How does that work?
Exactly. It does this by representing the random inputs and also the solution you're looking for, not as single values, but as expansions. It uses these special polynomials, like generalized polynomial chaos.
GPC polynomials?
Yes, GPC polynomials. Think of GPC as a sort of fancy basis set that's specifically tailored for representing random functions efficiently.
So the unknowns aren't the direct solution values anymore, but the coefficients of these GPC polynomials.
Precisely. And the original SPDE gets transformed into this huge system of deterministic equations for these coefficients. Then, when you discretize that in space using finite elements like you normally would,
Mhm.
boom, you end up with a single, enormous, coupled linear system.
Okay, enormous coupled linear system. That sounds like code for computationally impossible to solve directly.
It usually is, yeah. The matrices involved are just too big to store explicitly, let alone invert directly. So what does this mean in practice?
You have to use iterative solvers,
You got it, iterative solvers.
like Krylov methods, where you start with an educated guess and then refine it step by step towards the true solution.
Exactly. But the catch is, for those iterative solvers to converge quickly, especially on these massive SGM systems, they need help. They need a good preconditioner.
Ah, the preconditioner, the mathematical helper, doesn't actually change the final answer,
Like the solution stays the same.
but it sort of reshapes the problem, makes it easier for the iterative solver to find the answer much faster. It's like giving the solver a better map to navigate the problem space.
That's a great analogy. A good preconditioner essentially bunches up the eigenvalues of the system matrix, making the solver's path to convergence much more direct, much shorter. Without a good one, even these iterative solvers can just grind away for ages.
Okay, makes sense. And presumably, researchers have been working on preconditioners for these SGFM systems for a while now.
Oh, absolutely. There's quite a history. You've got simpler ones like the mean-based preconditioner.
Mean-based, how does that work?
It's pretty straightforward. It just uses the spatial matrix that corresponds to the average or mean value of the random coefficient. It ignores a lot of the stochastic detail.
Simple. Okay. Pros and cons.
Well, it's simple to construct, and its efficiency doesn't degrade as you refine the spatial mesh, which is good, but it can be slow because it misses so much of the coupling.
Okay. What else is out there?
Then there's the Kronecker product, preconditioner. A bit more involved. It tries to approximate the structure of the full SGFM matrix using a Kronecker product of smaller matrices, one spatial, one stochastic.
And that performs better.
Generally, yes. It captures more of the structure, so it often outperforms the simple mean-based one.
Fine.
And then people started looking at truncated hierarchical approaches. They recognize that the SGF matrix itself has this natural hierarchical block structure linked to the polynomial degrees you use.
Like layers based on the complexity of the randomness?
Sort of, yeah. And they tried simplifying or truncating parts of this structure. Things like hierarchical, symmetric block Gauss-Seidel methods. Those proved quite efficient in some cases.
And more recently, this idea of truncation preconditioners seems to have gained traction, just taking the big matrix and chopping bits off.
Pretty much. The idea is you build the preconditioner by keeping only the most important entries of the full SGF matrix, maybe based on their size, their magnitude.
Huh.
Throw away the small stuff.
Seems intuitive.
Well,
Simplify the problem.
it does, but here's where it gets really interesting and a bit tricky. Just picking the biggest numbers and throwing everything else away might simplify the matrix, sure, but it doesn't guarantee that the resulting preconditioner matrix has the same essential mathematical properties as the original full matrix it came from.
And properties like being symmetric and positive definite are super important, aren't they?
Yeah.
Why is that such a fundamental problem?
They are absolutely critical. Many of the most robust and, frankly, widely used iterative solvers, like the precondition conjugate gradient method, PCG, they fundamentally rely on these properties.
TCG needs the matrix to be symmetric positive definite.
Yes. PCG, for example, mathematically views the problem as minimizing an error in a special kind of norm, like finding the bottom of a bowl. That bowl is defined by a positive definite matrix. If your preconditioner isn't symmetric and positive definite, the geometry breaks down. You can't use PCG reliably. Its convergence might become completely unpredictable, it'd stall, or just fail entirely.
Okay. So it's not just about making the solver faster, it's about ensuring you can even use some of the best solvers reliably.
Precisely. And that brings us neatly to the core contribution of the paper we're digging into today. They propose two novel truncation strategies, specifically designed for common types of random inputs, with the explicit goal of both improving efficiency through smart truncation and, crucially, preserving those essential mathematical properties.
Okay, smart truncation. Let's break those down. What's the first one?
The first strategy is for what are called affine parametric coefficients. This type of randomness is, well, relatively simple in structure. The coefficient is basically a sum of terms. Each term is a spatial function multiplied by a single random variable.
Like a Carhoonen-Loewe expansion, if you've encountered that.
Exactly like that. It's a common way to represent random fields. Now, their novel strategy here is to decide which terms to keep and which to truncate, not based on the absolute size of those spatial functions, but on their relative size compared to the mean term. So they look at the ratio, say, am divided by a0, where a0 is the mean part.
Relative magnitude. Why? What's the intuition there? What advantage does that give?
Well, what's fascinating here is their theoretical analysis. They show that the convergence rate of the iterative solver, specifically how well the preconditioner clusters the matrix's eigenvalues, which dictates speed, is closely tied to a quantity they call error. Epsilon
R.
And this error measures the error you introduce by this specific relative magnitude truncation strategy.
So the smaller this epsilon R error is, the better the preconditioner is expected to work. Faster convergence.
Exactly. Lower error predicts sharper eigenvalue bounds, which predicts fewer iterations, and they found something quite neat. If you sort the terms by this relative magnitude, a mer, and then trumpate in a way that minimizes this error, that error decreases steadily as you include more terms in your truncation. This predicts better and better performance.
And how does that compare to just sorting by absolute magnitude?
That's the key difference. They show an example in their table 5.1, where just sorting by absolute magnitude results in an error that basically stays constant as you add terms. It doesn't predict improvement. But sorting by relative magnitude makes error decrease, predicting the better performance they actually observe later.
That's clever. So the truncation rule itself is directly linked to a quantity that predicts how well it should perform.
Yes, and they back this up with a strong theoretical result. The preconditioner built using this relative magnitude strategy is proven to be optimal with respect to the key discretization parameters.
Meaning its performance doesn't degrade badly if you refine your spatial mesh, or include more random variables, or use higher polynomial degrees.
Exactly. That's a powerful guarantee for practical use.
Okay, very interesting for the affine case. What are the other type they looked at? Log normal coefficients. These pop up a lot, right?
Yeah.
Especially in things like groundwater flow.
They do, because they naturally guarantee that the diffusion coefficient stays positive, which physical properties like permeability have to be. You can't have negative diffusion.
Right. So how does this strategy change for log normal?
Well, for log normal coefficients, it's the logarithm of the coefficient that has that simpler affine parametric structure, that sum of terms.
Ah, okay, so you work with the exponent.
Precisely. The truncation strategy here focuses on the terms in the exponent. The novel approach they propose, which they call Strategy 3 in their experiments, is to truncate terms based on the multi-index associated with the underlying random variables.
Multi-index, meaning the combination of random variables involved.
Yes. Specifically, they define a threshold R, and they keep only those terms in the expansion of the logarithm where the random variables beyond index R are not involved. So you're essentially limiting the complexity based on which combinations of the fundamental random parameters influence a term.
Okay, so you're grouping terms based on which underlying random variables they depend on and keeping the ones tied to the first R variable.
That's the gist, yes. And the critical mathematical benefit of this specific parameter-based truncation for log normal coefficients is, drumroll.
It preserves positivity.
Exactly. It is proven to preserve the positivity of the resulting truncated matrix.
Boom. There's that crucial property again, the one needed for solvers like PCG.
If we connect this back to the bigger picture, this means you can build your preconditioner directly from this truncated matrix, knowing it's positive definite. You don't have to worry about complex workarounds or checks to force positivity after the fact. It's built in.
That sounds much cleaner. And presumably, picking a small R value, keeping only terms depending on the first few parameters, also helps keep the resulting preconditioner matrix simpler, more sparse.
Yes, exactly. Sparsity is always good for computational cost. So once you have these smartly truncated matrices based on relative magnitude for the affine case, or this parameter index R for the log normal case, the next step is actually turning them into practical preconditioners you can use in a solver.
Right, because just having the truncated matrix isn't enough. You need to be able to apply its inverse efficiently. And this is where the hierarchical structure of the original SGMM matrix comes back into play.
Yes, that structure is key. The full SGF matrix naturally breaks down into blocks based on the polynomial degrees used in the GPC expansion. You can see it in their equations 4.1 and 4.2.
And they exploit that block structure.
They do. They build two specific types of hierarchical preconditioners using their truncated matrices.
Okay, what's the first one?
First is the hierarchical Schur complement preconditioner. This is based on a specific mathematical factorization, like a block LU decomposition of that hierarchical matrix structure. You can see the formula in equation 4.3. Applying its inverse essentially requires solving systems related to the diagonal blocks within that structure.
And does theory support this one?
Yes, for the affine parametric case where they have the rigorous analysis, their theory confirms that this type is also efficient. Its performance is independent of the spatial mesh size, H, and the number of random parameters, M, you include.
Okay, optimal again. And the second type?
The second is the hierarchical symmetric block Gauss-Seidel preconditioner. This isn't an exact factorization, but an approximation of the truncated matrix that also uses that hierarchical structure, as in equation 4.8. Think of it like doing block Gauss-Seidel smoothing within the hierarchy. Applying its inverse also involves solving with those diagonal blocks.
And the theory for this one?
Same story for the affine case. Like the Schur complement type, this one is also proven theoretically to be optimal with respect to the discretization parameters, h, m, and polynomial degree k.
Okay, so we have these two novel truncation strategies, one for affine, one for log normal, designed to be smart and preserve properties. And we have two ways to build practical hierarchical preconditioners using these truncated matrices, both with good theoretical backing, at least for the affine case.
Exactly.
So what does this all mean in practice then? Let's talk computation. How do these actually perform when you run the numbers?
Right, the bottom line. The total time to solve the system with an iterative method like PCG is basically, the number of iterations it takes to converge.
Times the cost of doing one iteration.
Times the cost of applying the preconditioner's inverse in each step. Exactly.
So let's break down that cost per iteration for the different methods.
Okay. For the simple mean-based preconditioner, each iteration involves solving systems related to the basic spatial stiffness matrix, K0. You have to do this a number of times proportional to the dimension of the stochastic space. Let's call it n infinity.
N infinity.
Yeah.
That's related to the number of polynomials used.
Yes, it grows with the number of random parameters in the polynomial degree. For the Kronecker preconditioner, it's more complicated. It involves solves with chi0, but also with a matrix related to the stochastic part, G. And for log normal problems, solving with G can actually be quite expensive itself.
Okay. And the new hierarchical ones.
The proposed hierarchical preconditioners, both the Schur and the Gauss-Seidel types, require solving systems related to their diagonal blocks. Now, these diagonal blocks look very similar, often identical to that base spatial matrix K0. You need to solve with them roughly 2 times n infinity per iteration.
Ah, so the cost per iteration looks comparable to the mean-based one, maybe slightly higher, but crucially, it avoids that potentially expensive solve with the G-matrix from the Kronecker method.
Exactly. And if you have an efficient way to solve systems involving K0, which is standard practice in finite element methods, people use techniques like multi-grid or domain decomposition, then the cost per iteration for these novel hierarchical methods is very competitive.
Okay, so the cost per iteration is manageable. The big question then is, do these new preconditioners reduce the number of iterations significantly?
That's the million-dollar question. And that brings us to the numerical experiments they conducted. They used a software package called SIS, setting up standard diffusion problems on a square domain, first with affine parametric randomness, then with log normal randomness to really test their strategies.
All right, let's look at the affine parametric results. Test problem 1. Here they compared the simple magnitude-based truncation, let's call it strategy 1, against their novel relative magnitude-based truncation, strategy 2.
First off, table 5.1 directly validates their theory about error. For strategy 1, absolute magnitude, error is basically constant as they add terms. But for strategy 2, relative magnitude, error decreases significantly, just as predicted.
Okay, theory holds. What about the actual solver performance? Tables 5.2 and 5.3 show iteration counts and time.
Yes, and the payoff is crystal clear. For strategy 1, the performance measured by iterations and time basically plateaus or only slightly improves as you add terms. It behaves much like the basic mean-based preconditioner.
What's strategy 2?
Strategy 2, the novel one, based on relative magnitude, consistently leads to decreasing iteration counts and decreasing overall solution time as they include more terms. Increase R. It clearly benefits from adding more information via that smart sorting.
So, conclusion for a FEM.
Strategy 2 significantly outperforms Strategy 1 and the baseline mean-based method for this problem. The results align perfectly with what their error theory predicted. Sorting by relative magnitude really works here.
Very compelling. Now, what about the log normal results? Test problem 2. This seems like maybe the trickier case. Here they compared mean-based, Kronecker, and different truncation strategies, including magnitude, degree-based, and their novel parameter-based one, strategy 3.
Right. And if you look at tables 5.4 and 5.5, the results for strategy 3 are, frankly, dramatic.
How so?
Strategy 3, the parameter-based truncation, example using R1 or R2, consistently achieved dramatically lower iteration counts compared to both the mean-based and the Kronecker preconditioners. This holds true across different polynomial degrees. We're talking huge reductions, sometimes needing only a tenth or fewer iterations.
Wow, so it's not just a little bit better, it's potentially an order of magnitude fewer iterations in some of these cases.
Exactly. While some of the other truncation ideas, like magnitude or degree-based, might offer marginal improvements over mean-based sometimes, strategy 3 provided by far the most significant performance lead.
And even considering the cost per iteration we discussed.
Oh, yes. Even though the cost per iteration for strategy 3, using the hierarchical solvers, is similar to mean-based, those drastically lower iteration counts mean that strategy 3 leads to the fastest overall solution time compared to both mean-based and Kronecker. The numerical evidence here is really strong.
Okay, that really underscores the benefit of that parameter-based truncation for log normal, the one that also guaranteed positivity.
It seems highly effective.
Okay, let's try and bring this all together then. What are the main takeaways from this deep dive into these preconditioners?
Well, first, SGF is a powerful tool for quantifying uncertainty in simulations involving PDEs, but it generates these absolutely massive linear systems. That's the bottleneck.
Right, solving those systems efficiently is the name of the game.
And the key to solving them efficiently is a good preconditioner. Standard ones exist, but there's room for improvement.
And this paper introduced and importantly validated novel truncation strategies for building those preconditioners. They're specifically tailored for affine parametric and log normal random inputs, which are very common in practice.
Crucially, these strategies are smart. They don't just, chop off terms arbitrarily. They truncate in ways designed to preserve essential mathematical properties, like positivity for the log normal coefficients.
Which is vital for reliable solvers, like PCG.
And also to improve the spectral properties that govern convergence speed, as demonstrated theoretically and numerically for the affine parametric case using that error measure.
And then, when these clever truncation ideas are actually used to build practical hierarchical preconditioners, like the Schur complement or symmetric block Gauss-Seidel types.
The resulting methods have excellent theoretical properties, suggesting their efficiency should hold up well, even as you scale up the problem size or complexity. At least the theory for the affine case is solid on that.
And the numerical experiments really backed it all up, didn't they? Showing significant, sometimes really dramatic reductions in the number of iterations and the total time needed to solve these complex SPDE problems compared to previous methods.
Yeah, the numbers look very promising.
So, bring this back to you, the listener. Why should you care about all these technical details of truncation strategies and hierarchical preconditioners?
Well, because if your work involves simulating complex physical systems where uncertainty is inherent, maybe you're designing safer structures under variable loads, or optimizing energy extraction from a heterogeneous reservoir, or predicting environmental change with uncertain inputs.
Basically, any field using complex simulation.
You need simulations that are not only accurate, but also fast enough to be useful. You can't afford to wait weeks or months for a single simulation run, especially if you need to explore many scenarios.
Right. Time is critical.
Advances like these efficient, property-preserving preconditioners are what make those complex uncertainty quantification studies computationally feasible. They're kind of the unsung heroes that let us get reliable answers from sophisticated models in a reasonable amount of time. They bridge the gap between theory and practical application.
Well put. Okay, before we wrap up, any final provocative thought for our listeners to chew on based on this research?
Yeah, actually, it's something the source material itself mentions. While they have strong theoretical results explaining why the relative magnitude strategy works so well for the affine parametric case, they explicitly note that future work is still needed on the theory for the log-normal diffusion coefficients to fully investigate the robustness of their parameter-based strategy, strategy 3.
Oh, interesting. So even though the numerical results look fantastic.
Exactly. Think about that for a moment. They have compelling numerical results showing this log-normal strategy works incredibly well in practice, leading to huge speedups, potentially saving enormous amounts of computational time. But the complete, rigorous mathematical proof explaining why it's guaranteed to be robust and work so well across all possible scenarios for log-normal inputs, that's still an open area of research.
So practice is maybe a little ahead of the full theory in that specific case.
It seems so. It just highlights that fascinating space, even in advanced computational math, where practical computational success sometimes runs ahead of our complete theoretical understanding. It shows there's always more to discover and rigorously prove, something to chew on.